Let's jump right in. Welcome to this explainer. Today we're cracking open IS 456-2000. Now, if you're here, you already know this is the definitive code of practice for plain and reinforced concrete in India. We're skipping the basic 101 stuff. We're diving straight into the hardcore science, the rigorous testing, and those absolute mathematical boundaries that literally dictate modern structural engineering. We're going to unpack this standard, chapter by chapter, to really understand the non-negotiable rules engineers rely on to safely build the spaces we live and work in every single day. But before we get completely lost in the heavy engineering, I want to frame our discussion with some ancient wisdom. Knowledge is such a treasure which cannot be stolen, as written by Bhartrhari. It's actually a perfect parallel to the modern Right to Information Act. Because think about it, engineering codes like IS 456, they aren't just private, locked-away rulebooks for contractors. They are quite literally public treasures. They exist to safely build a nation. And having transparent access to this knowledge is fundamentally about public safety and empowerment. And that ties perfectly into Sam Pitroda's famous call to invent a new India using knowledge. Taking that spirit, stepping out of the old and into the new, we are going to break down this highly technical standard. We'll take those complex tables and rigorous structural mandates and translate them into crystal clear concepts. You'll see exactly how this specific knowledge shapes the physical world around us. All right, so here is our roadmap for today. First, an introduction to IS 456. Second, concrete materials and mixes. Third, rules for reinforcement. Fourth, designing special structural members. And finally, permissible stresses in concrete. Let's get to it. Starting right off with Section 1, Introduction to IS 456 and its general scope. This very first section lays down the absolute boundaries of the code. Take the definition of plain concrete structures, for example. In these structures, any internal steel reinforcement, even if it is physically right there in the concrete, is mathematically ignored when you calculate overall strength. It's this beautifully conservative engineering principle. It basically forces the design to ensure the concrete alone can bear the intended load completely without relying on the steel. But here's the catch. It is equally crucial to know what this code does not cover. Highly specialized projects, things like arches, bridges, blast-resistant structures, or earthquake-resistant buildings, they all require their own dedicated codes. You just can't use IS 456 in isolation for those. Instead, you have to pair this general standard with specific specialized codes to ensure bulletproof safety for those complex, dynamic loads. Moving right along to Section 2, Concrete Materials and Mixes, covering materials, workmanship, inspection, and testing. This is where the code regulates the actual recipe of the concrete itself. Because obviously, a sturdy building begins with the right core materials. It's exactly like a highly precise baking recipe. Section 2 strictly dictates the quality of 4 main ingredients: the cement, any mineral admixtures you're throwing in to alter the concrete's properties, the aggregates, your sand and crushed stone, and finally, the water. If literally any of these components are compromised on site, the entire structural integrity of your project is at risk. Now, this is where it gets really fascinating. Look at how environmental exposure directly dictates your precise mix. As the environment gets harsher, shifting from mild all the way down to extreme, the required minimum grade of concrete shoots up, from M20 to M40. But I really want you to look at that maximal water-cement ratio. Why does extreme exposure demand a super tight 0.40 ratio? Well, it's to make absolutely sure the concrete is incredibly dense and less permeable. That is essential to stop moisture from seeping in and corroding the internal steel reinforcement. All right, let's dive into Section 3, Rules for Reinforcement and General Design Considerations. So, we have our concrete mix dialed in perfectly. Now, this section comes in to strictly mandate the geometry and placement of the steel. It tells you exactly how steel reinforcement has to be spaced out, precisely how much concrete needs to cover that steel, which we call nominal cover, and how structural stress safely develops and transfers between the steel and the concrete. That transfer is what ensures the building doesn't just snap under tension. It is, quite honestly, a highly choreographed arrangement of metal and stone. Next up, Section 4, Designing Special Structural Members, which covers deep beams, slabs, and footings. The math here gets incredibly specific to guarantee safety. Take calculating the lever arm for a deep beam, for instance. Based on this rule, engineers actually have to calculate 2 different values. the center-to-center distance between the supports, and 1.15 times the clear span between those supports. Then, the code mandates that you use whichever value is smaller. It's a deliberately conservative approach that guarantees your design is always accounting for the absolute worst-case mechanical stress. And mapping out critical shear sections in flat slabs is just as rigorous. Engineers have to do this to prevent what's called punching shear failure. That is a catastrophic event where a column literally just punches right up through a flat slab. The critical section calculation completely shifts depending on the exact architecture, like whether your flat slab has drops or if your supporting column has a flared column head. The code leaves absolutely zero room for guesswork here. Finally, we hit Section 5, Permissible Stresses in Concrete, specifically Annex B, the working stress method. So the bottom line here is how you match the exact grade of concrete to its safe compressive limits. You can see that an M15 grade concrete has a permissible bending stress of 5.0 newtons per square millimeter. But if you upgrade to a stronger M40 mix, that jumps all the way up to 13.0. By religiously adhering to these strict numerical limits, engineers ensure that every single column, slab, and beam can safely carry its intended load, not just for a few years, but for decades to come. We've covered a lot of ground today, journeying all the way from the philosophical importance of shared knowledge to the exact, non-negotiable mathematical stress limits of reinforced concrete. The knowledge is now in your hands. So I'll leave you with this. The next time you pour a mix, ask yourself, does your design truly account for these ultimate limits? Thanks for joining me on this explainer, and keep building smart.